Today, we are diving deep into a pretty radical new idea, one that might just challenge everything we think we know about the universe. It's called the dilational flooding model. So let's start with a really big, provocative question. You know how our standard model of the cosmos needs two really mysterious things, dark matter and dark energy, to work? Stuff that supposedly makes up 95% of everything, yet we've never actually found it. But what if they aren't missing pieces of the puzzle at all? What if we're just looking at the whole puzzle completely wrong? All right, so here's our roadmap for this explainer. First, we're going to look at the cracks in our current cosmological model. Then we'll take a step back and revisit the foundations laid by giants like Einstein and Hubble. After that, we'll introduce this new idea, the dilational flooding model, see how it claims to solve those big cosmic puzzles, and finally, we'll look at what this all means for the future of cosmology. So let's start with the problem. Why are scientists even searching for an alternative? Well, it's because our best theory, as amazing as it is, has some pretty significant tensions, as they call them. Our standard model is called lambda-CDM, or lambda CDM, and to make the math actually match what we see through our telescopes, it has to include two huge unknowns. Lambda represents dark energy, right? This mysterious outward force that's supposedly making the universe accelerate. And cold dark matter is the invisible mass that's meant to be holding galaxies together. Basically, these are exotic solutions that were added to the model to fix the parts where it didn't line up with reality. Okay, so to really understand a potential new way forward, it really helps to look back at the context in which our current path was even chosen. And the story starts with some surprising doubts from the giants of cosmology themselves. You know, it's a fascinating piece of history that a lot of people don't know. Both Albert Einstein and Edwin Hubble were really reluctant to accept a universe that had a specific beginning. They personally preferred the idea of a persistent, eternal cosmos. The great irony, of course, is that their own incredible work on relativity and cosmic redshift ended up becoming the cornerstone evidence for the Big Bang model they were so unsure about. And this timeline really shows you the pieces of the puzzle they were missing. Back in the early 20th century, there was zero proof of a cosmic beginning and absolutely no evidence that gravitational waves were real things, carrying energy through space. Then, in 1965, the cosmic microwave background was discovered. Huge evidence for beginning. But the real game changer, that came in 2017. LIGO directly detected gravitational waves moving at the speed of light, confirming a physical reality that even Einstein himself had his doubts about. This new information forces us to ask, what old assumptions should we now go back and question? And that very reevaluation leads us straight to this new proposal, the dilational flooding model, or DFM for short. Okay, this is the absolute core of the idea. DFM offers a totally different explanation for the redshift we see from distant galaxies. The standard model says redshift happens because space itself is stretching, right? And that stretches the light waves as galaxies move away from us. But DFM says, hold on. It proposes that redshift is actually an effect of time dilation, caused by our own local gravitational environment becoming denser and denser over cosmic time. So how does that work? Well, in a universe that has a beginning, our cosmic horizon, the absolute edge of what we can see, is always expanding at the speed of light. And as it expands, the gravitational pull from more and more distant matter can finally reach us. The best way to think about it is like our little patch of space-time is slowly being flooded by the gravitational potential of more and more of the universe's total mass. And this isn't just a vague concept. It's grounded in physics we've understood for centuries. This equation here, it really just combines Newton's classic inverse square law for gravity with the simple geometry of an expanding sphere. It shows that as the radius of our observable universe, that's our max, gets bigger, the total gravitational force we feel from all that new mass increases. And here's the crucial part. It increases in a simple, linear way. This is profound, because that linear increase in gravity perfectly mimics the constant expansion rate from Hubble's law, but it does it without needing space itself to expand one bit. Okay, so we've got a new model built on some old established physics. The million-dollar question is, does it actually work? Let's see how DFM stacks up against the standard model when it comes to explaining those cosmic tensions we talked about. Now, the guiding principle here is something called parsimony, or you might know it as Occam's razor. The basic idea is that the simplest explanation, the one that doesn't need to invent a bunch of new stuff, is usually the best one. And DFM's whole goal is to be that more parsimonious solution. So let's start with the Hubble tension, this big disagreement over how fast the universe is actually expanding. The standard model is really struggling to make the different measurements match up, and it might even need some totally new physics. But DFM says, wait a second, there is no actual acceleration. The speeding up we think we see in distant galaxies, it's just a predictable effect of time dilation. Remember, general relativity tells us that time runs slower in stronger gravity. So as our local gravity has been flooded and increased over billions of years, looking way back into the past is like looking at a universe where time ran just a little bit faster. This creates the illusion of acceleration with no new physics required. And what about that James Webb Telescope puzzle? Finding galaxies in the early universe that look way too mature, way too developed? Well, DFM offers a really elegant solution. Because light from the distant past comes from a place with a less cumulative time dilation, our calculations for how far away they are just a little bit off. DFM predicts these galaxies are actually closer, and, therefore, hundreds of millions of years younger than we think. And that extra time? It easily explains how they got so big, so fast. And then there's the big one, dark matter. It was invented to explain why galaxies spin so fast they should fly apart. LCDM solves this by surrounding them with huge invisible halos of dark matter. But DFM offers a different path. It says the constant dilational flooding of gravitational potential over billions of years just keeps making the galaxy's gravity well deeper and deeper. This perfectly mimics the effect of having extra mass, creating those same rotation curves without us having to invent a single new particle. And it doesn't stop there. DFM also has plausible explanations for the other big cosmological tests, the very things that seem to lock dark matter into the standard model. Take gravitational lensing. DFM says it's not just caused by the mass that's there now, but by a gravitational field that changes over time. Or the bullet cluster, the so-called smoking gun for dark matter. DFM argues that what we're seeing is a kind of historical, frame-dragged gravity, a ghost of past gravitational influence, not a clump of invisible matter. It even has potential answers for the large-scale structure of the universe and the patterns in the cosmic microwave background, all by just applying physics we already know in this new context. So where does all of this leave us? Well, the dilatational flooding model presents a new path forward, a testable one, that really challenges us to rethink some of our most fundamental assumptions about how the universe works. Really, the core strength and the biggest appeal of DFM is its simplicity, its parsimony. It doesn't throw out the rulebook, it just rereads it very carefully. It tries to solve cosmology's biggest problems by going back to the first principles of Newton and Einstein, but applying them in a finite age universe where gravity's influence can only travel at the speed of light. No dark matter, no dark energy. And this really leads to a powerful idea that comes from the source material. Maybe the best way to move forward is to look backward, to revisit the context of our past successes, but this time armed with all the new things we know today. Which leaves us all with this final lingering thought. Could it be that the solutions to the universe's greatest mysteries don't require us to discover exotic new particles or forces, but simply demand a deeper, more complete understanding of the incredible physics we've had all along?